So I welcome everybody to my talk about the Intel 4 Mod 4, the world's first commercial available microprocessor and its application. It's quite an honor to talk about this topic because it was really a technology milestone at that time. And here you see two of the most important characters in the early history of Intel. Imagine that the company Intel only produced memory chips in the late 60s. And there was the company VCFe, and the company VCFe produced calculators. And they asked Intel if Intel could produce a chipset for this calculator. And at Intel, they looked over the plans of VCFe and figured out that there was a better way, a more generic way. And this was actually the birth of the first chipset with an integrated CPU. On the right side, you can see Masatoshi Shima from the VCFe company, and on the left, Federico Faccin, who had been hired by Intel after Intel promised VCFe to produce the chips. Now, no work was done at all at Intel before they hired Federico Faccin. And then, shortly after he was hired, Masatoshi Shima came to visit and to look at Intel what has happened so far. And not much. So there is a famous YouTube video where Federico Faccin tells himself what happened. So Masatoshi Shima arrived, looked at Federico and said, "You are bad, you are bad." And in the end, he calmed down and convinced his company to let him stay for, I think it was 6 months. And Masatoshi Shima helped Federico Faccin in designing all the chips. So how did I come actually to all the information to rebuild the VCFe prototype? There was a lot of work already done by a team led by Tim McNerney. Tim McNerney, I got in contact with him via HackerDay.io because I looked at some schematics of an already rebuilt prototype replica, and I didn't understand something with a strange transistor in there. It was the build of Bill Katoska, and he put some protective circuit onto the data lines, and he said, okay, this is a transistor, and actually should have pulled the data lines up to 0.7 volts, and this didn't make sense to me. And there I was at HackerDay.io, please help, can anybody help me? And Tim McNerney then wrote, yeah, here you have my email, and then I told him what I was up to. And together we figured out also on Stack Exchange that this is a Darlington pair, and so the circuit made sense. And Tim, I will later talk about these people. So also yesterday we had a visit of Professor Klaus Scheffler, and he showed his discretely built 4 Mod 4 with discrete transistors. This was the initial announcement of Intel, the initial advertisement. Imagine you only had this big mainframe computers, and that's actually how this chipset is depicted here. I find it quite funny. So all the computational power of these big mainframes is now incorporated in one single microchip. This is the internal architecture of this 4 Mod 4. So I should have brought a laser pointer. So here you have the register file consisting of 16 4-bit registers. Then you have a stack, which is not actually a real stack. It is more like 4 separate program counters. And the multiplexer then tells you which one is incremented and which ones are not. And if you write an emulator, where we will come to later, it is very crucial that you implement the stack in the right way, because there is also a test program and there's even software that uses this strange implementation of the stack. So you have like 3 levels you can push, and if you push a 4th time, then this kind of stack behaves in a certain way. And if you implement it differently, then the software will not work. Then you have instruction decoder, machine cycle encoding. You have a very simple ALU that can do additions and subtractions, and not quite much more. This is the way actually these 4 chips work together. On the top, you see the 4-mode-4 microprocessor with 4 data line pins. Unfortunately, there it is. 4 data lines, and these connect to the 2 other peripheral chips. The 4-mode-2 is the RAM chip, and the 4-mode-1 is the ROM chip. What makes these chips special is also that the RAM chip has output ports, and the ROM may have input or output ports. Then there is a 4th chip, the 4-mode-3, which is a shift register. It's a 10-bit shift register, and this one works completely asynchronous, whereas the other chips have a synchronous input, and this is driven by the CPU. So here you input a 2-phase clock that must not overlap. Then the CPU generates a sync output, and this goes into the other chips. Then the other chips know in which part of the instruction cycles we are. The calculation power was quite okay at that time. You can add 2-digit numbers in 850 microseconds, and the overall instruction cycle was around 10 microseconds. The voltage the system used was actually low at that time. There were also MOS chips that needed almost minus 20 volts. This had also to do with the gate thickness of the transistors they could build. And one funny thing is that up to that time, Intel only produced these memory chips in a 16-pin DIP package, and it was like a religion at Intel, and they didn't want to use larger packages. And that's why Federico had to do quite a bit multiplexing. Here you see the pinout of the 4-mode-4 CPU. And on the right, I have a schematic table on how to couple the RAM onto the CPU. On the CPU, you see you have 4 CM-RAM outputs. These are control outputs. It's like a chip select for the RAM chips, except it works a little different. And here you have 4 data bus signals. It is so that you have 2 metal options of the 4-mode-2. This means that when the chip coming from the fab and has the -1 marking, it only decodes for chip numbers 0 and 1. And if you buy the -2 chip, then it only decodes chip number 2 and 3. Then to distinguish between 0, 1, 2, and 3, you have the P0 input. Where is it? This is the CPU. We will see it on the next slide. And the P0 input can either be GND or -15 volts. And this corresponds to this upper 2 bits on the X2 phase. I will also explain the phases in the next slides. And there you could add up to 4 memory chips per CM-RAM. So if you only have these banks directly on the CM-RAM signals, you can have 4 memory banks, A4 chips. And if you put a demultiplexer, then you can have 16 memory chips. 16 banks. 16. No, you can even have more chips then, yeah. So you have the ROM chip on the right, and this have I/O ports, and these are already pre-configured also in the factory. So you had to tell Intel if you want an input port or an output port, and you could specify if you want to have a pull-up resistor or not. And also the content, of course, was stored there by metal mask during fabrication. And if you wanted to develop the system you wanted to test code, then you wouldn't have Intel let you produce you the ROMs. However, you wanted to put PROMs there, and there were adapter boards where you could develop with standard PROMs or even paper tape. Then there was the 4-mode-2 RAM I just talked about. And here it has the P0 input for the chip select decoding. And here you have the clock input, the data lines, and here you have the I/O output lines. And also needed for the decoding, more important, the control input. The 4 mode 3 shift register works asynchronously. You have to put data onto data in pin, and then you can activate the clock pulse. And this can actually happen at the same time because they have a built-in delay loop. And this is very convenient because then you only need 2 output ports, for example, of the RAM, and can control this shift register. And then you have an enable input, if it takes serial data or not, and you can even cascade them with the serial output. This is how this whole machine cycle then works. We have this overall machine cycle time of around 10 microseconds. And you have different cycles. First, the CPU will output the instructions in 3 clocks. The address in 3 clocks. Then it will fetch the machine instruction from the ROM. And then in these later 3, it will actually execute the instruction. This is a diagram of how the control lines work. Every time you have this dip, the chip is active. So the CM-ROM line here is active. With a 4 mode 4, you only have 1 ROM bank. And this means the program data is fetched from this ROM bank. And it has to be active on the last address clock cycle. Also, there is usually 1 RAM chip active. And why this? Why is this? Because the RAM also decodes part of the instruction. It is not like with modern RAMs that you have a generic address sent to the RAM and then just data comes from the RAM. But the RAM instead interprets a command. And with this command, then you can also set the output ports of the RAM. In this example, the first instruction the CPU executes is the DCL instruction. This is an important instruction to address memory. It's called designate command line. And there is an internal register in the CPU that then outputs the content of the command line register. And this is then used in the address. And this is then used for the chips to tell them if they are selected or not. Then you have a source instruction in the next cycle, and the source instruction tells the CPU to fetch the address and output it onto the address line in the following instruction. And this I/O instruction here then possibly tells the RAM to output data or the ROMs to input data. Depends on what you want. Here is an overview over the register file. So you have single bit registers. Wait, this is not register file, I'm sorry. This is instruction format here. You have 2-word instructions, for example, those who work with the memory, or you have single-word instructions, for example, those who modify the accumulator. And if you output an address, first the highest nibble of the address is output, and then the middle and the lower address is output. You have conditional commands that work, like a jump instruction, where you always jump inside the currently active ROM, so within 256 bytes. And this bitcode tells the condition of the jump. And then you have register instructions that fetch data or put data, and these usually work with a register pair to fetch a byte, because one register only can hold 4 bits. And then you work with register pairs. This is usually done if you have an X here. It's either 0 or 1, depending on the instruction. And these upper 3 bits then address an even number of a register, which is then interpreted as a pair. Here you see the different instructions you use to address RAM and ROM. For example, with the WRR means write ROM, but it's an I/O operation. So it's of course you cannot write to the ROM contents. The 4 mode 2 WR0 command, for example, is a special command because the RAMs are organized in a certain way. You have like a usual register file, and then after each register you have a certain separated memory location. You could, for example, store the digits of a number into the usual part of the RAM, and write to this with a WRM, and these others are then accessed with these instructions, and the same for reading. So the RAM design is quite horrible. And here is an example on how to actually program this. LDM means load accumulator. Exchange here means exchange the accumulator with register 15. LDM6 means load 6 into accumulator, exchange it with register 14. And then you do a fetch immediate from ROM into register 0. It's actually a register pair. And you do this data you fetch from the ROM then immediately follows. So you load this number here into these are 4-bit numbers. You load them into register 0. And then you execute the source instruction, and this means that you send the address in the next address access cycle out that is in this register because you put the 0 here. And then you can actually use a memory instruction like WMP and write the content of the accumulator to the output ports that was selected by the source instruction. This is quite an instruction overhead. This is how the die looks like. If anybody of you has seen the discrete PCB version yesterday, then you can recognize, for example, here the MOSFETs of the shift register for the 8-bit instruction cycle parts. Here the register file, here the ALU, in the middle the instruction decoder, and the stack somewhere. So I wanted to build a system with this CPU, and the first thing you have to think about is what is the minimal system. The minimal system you can build consists of a CPU, a RAM, and a ROM. So the RAM chip has 4 outputs, and the ROM chip has input and output, possibly, and you have a 2-phase logic, and you have a 4-bit data bus. So with this, you have the first problem, because you cannot get 4 mod 1 with the program you desire. However, let's continue this for a moment. You could then control with the output of the 4 mod 2 a shift register. And with that, you could actually already control a keyboard. For example, you could put a bit in the shift register, shift it around the columns of a keyboard, and if it has 4 rows, you could then read which row is active into the ROM. This was like it's done in the VCFe calculator. And another additional chip we see here is the clock generator. On the original calculator, you have a discrete transistor circuit that generates the clock, and this is more convenient. It was actually invented a little later and is also used for single stepping in the 4040. As I said, we don't have any 4 mod 1 with our program, so we need to use standard ROMs like the i702, 1702, and you can only address a standard ROM if you have some kind of adapter chip. And this chip, you either had the option to use the 4 mod 8 and 4 mod 9 for I/O, or to use this chip that combines 4 mod 8 and 4 mod 9 into one chip. This was also designed for the 4040 system. So with this design, we have actually replaced the ROM and with another ROM, and this ROM has the same capacity, namely 256 bytes, and it has TTL outputs. So what this chip also does is it translates from the MOS levels, because this system on this side now, we have minus 15 volts here, and if you go with this chip over to TTL logic, you have to introduce a ground between the minus 10 then and plus 5, because you need plus 5 for TTL. So instead of 0 and minus 15, you use +5, ground, and -10. And this chip has two different VDDs, two different VDD levels, and with that you can then drive TTL logic. Here are the logic levels again. So we get something near 5 volts for logic 0 because it's negative logic. The 4 mod 4 is PMOS technology, and for that negative logic is standard or more natural. So everything is reversed. And the logic 1 you get the more negative logic like -7 volts. And these are of course invalid levels for TTL. So one very difficult thing for me was to figure out how does it really work to interface TTL chips to this MCS4 family without producing smoke. And there was something depicted in the data sheet. And in the data sheet, they just showed, oh, you can put a pull up to -10 volts, actually a pull down, on the output of the MOS device, which has this push-pull logic output, and then it will work fine with an input of a TTL. But I didn't trust this, and then I built a small test system and measured with an oscilloscope, put a small ROM with this loop that alters a RAM output port, and then measured what happens. So these two chips actually, I used some random TTL chip, and the first thing I looked at what happens if I put this resistor here. Without the resistor, I got 5 volts and -7.5 volts for logic 1. And as soon as I put the 12K resistor, I got 4 volt and -10 volt, so -10 even worse for a TTL. If I put it onto the TTL, so here we have the -10 volts, and usually think, oh, the TTL is destroyed then. However, to drive a TTL low, so if it's open, you have a logic high. And if you want to drive it low, you have to sink a current from the input of the TTL. If this current is too low, then the input will not go too low. And this is actually what happens. You get something like 0.7 volts, so nothing happens. This was already promising. Then I combined everything, and then I saw, okay, I get something like -0.4 volts and 5 volts. So it worked actually completely as Intel designed it in this data sheet here. So we need no level shifter, we need no clipping diodes, we need no active compensation. However, we have to make sure that we use 47, 47S or 47LS TTL chips. No HCT or HC, because we don't want CMOS. On CMOS, you would have only gate inputs where no current flows, and the gate will probably be destroyed. So now, based on the design of Lajos Kindli and Bill Katoska, who rebuilt one prototype with a real drum printer, I was able to modify their design and build my own replica. And I simplified the printing simulator. He used a PIC. I'm not familiar with a PIC, so I used an Arduino. And what I did more complicated is I wanted to have EPROMs from that time, not like 2780, or 8 or 16, but I wanted to use 172 EPROMs. And this was then the layout I did. So here you have the 5 EPROMs. Here you have the 4289 adapter chip. Here the CPU, then 2 RAMs, 3 shift registers. These 3 are glue logic. And then here I have the keyboard interface, the printer interface, and the rest are just resistors. Here the clock generator and the quartz. This is part of the schematic. Here you have the standard memory interface, and it's actually a kind of an address latch. And here, so it stores, you get the address in nibbles, input here serially, and then you have the complete address latched here. And this, the C outputs then, it's the uppermost nibble, goes into a usual demultiplexer, like the 138. And with that, you can drive the chip select signals from the EPROMs. The rest is just glue logic. By using this beauty here, you have to figure out a way how to actually program it. And this is really quite a thing, because it needs almost 60 volts. And And the voltages when programming are completely different from the voltages when reading. That's why a lot of programmers from that time were two-socket design, where you had to change the sockets. And Intel really did a one-socket design, but they had to use a lot of transistors for switching the pins. The 1702 without A needed 20 minutes to program. You cannot obtain them anyway. And with A, you can get quite a lot of on eBay still, like for 50 euros a piece. And it programs in 2 minutes. And it's really quite reliable for that age. This was the first try. There was a guy on internet called Stephen Lafferty, and I wanted to rebuild his design. His programmer was driven by a parallel port, and I thought I would be good enough to add a microcontroller and switch my voltages with relays, and then go over serial and to USB. And then what happened is it just made boom, and I had like 60 volts on my USB port. Well, the laptop still worked, thanks God. But then I didn't want to continue for quite a while. Then I found another design made by Matt Millman. And Matt Millman was like a hardcore designer. I can do everything in SMD. I can do it very small and compact. And yeah, I never had done any SMD before. So these are 200 SMD parts. You had to find them. You had to find alternative parts. And I built this. It took me 4 days to solder. And then, of course, it didn't work because I had some short circuits. And then almost before throwing it onto the wall, I succeeded in debugging it. And I was able to burn my first EEPROM. And you even can hear it when you burn it. And there are already 2 others who built this. And Matt himself was really surprised. Oh, there are really people who built my design. Haha. Yeah, I'm quite thankful for his design. But how do you get to the firmware? Well, thanks to efforts of Tim McNerney and his team. So here come the names in. Dag Spicer, the chief content officer of the Intel Museum, allowed Tim's team to enter the museum and pull the ROMs of the original prototype. And Tim had constructed a ROM reader, and he was able to read the complete firmware. And so this was the first step. And then the Silverman brothers were able to completely reverse engineer it. And they have really great comments in the firmware. So you can, if you spend enough time, you can understand the complete firmware. And then another guy, Christian Bassau, also had some nice pictures. And Fred Hüttig with him, he made the Schaltplan circuit. So they reconstructed the whole circuit of the calculator to know where do the hammer signals come from, where do the keyboard signals go. And with that, the first prototypes replicas were rebuilt. And then I used some SatMagic, my own assembler, and the Millman burner, and reburned it into the EEPROMs. But before I wanted to really build it, I wanted to make sure if the polarities of the signals are correct. And for that, I wanted to build my own simulator. And the simulator should be C, because I hate Java. There are already Java simulators out there quite good, but I really dislike Java. Then I wanted to simulate on bus level, not on transistor level or some crazy thing. And I wanted to make it quite exact, so within one sub-phase of one clock cycle. Then I wanted a simulator that works in Linux without any emulation of Windows and stuff, or even .NET. And then I wanted to use some standard techniques like POSIX threads. I wanted to simulate RAM, ROM, and CPU and put everything into its own thread, so that I could also emulate other systems, because then I could connect chips in a different way. And I wanted to have this generic approach. And the code then looks like this. I don't know if you can read it. So I have like structs in C that represent objects. Then I initialize, like here, a ROM and I have in every struct, it's like polymorphism in C++. I use some common type that every struct has, and then via pointer conversion, I can do something like object-oriented programming in C. Then I use a ROM buffer to load the data into the simulated ROMs. And here I really simulate then the 5 ROMs of the BCCOM. And here are the RAM chips. And so I have a context variable for the simulator. I have this polymorphism thing, and I have the chip number. And I simulate the circuit and the chip select lines. And here I connect callback functions. So if some RAM, for example RAM 0, outputs on bits number 0, then I know this goes to move printer ribbon. And this then calls the callback function with a value, and then I'm able to simulate the behavior of the circuit. Then this is an example of how I implemented the behavior of the chips themselves. For example, this gets executed on every phi1 clock cycle, and this on phi1 A2 subclock cycle. And here I modify the CPU internal stuff and things like that, and the stack. So then now I want to do a simulator live demonstration, and with that you can actually see on the left. Does it go on the left? Yes. You can see what's going on. I hope the resolution is large enough. Yeah, barely. Shit. I have to increase the... Because the most important stuff happens on the right. I have to... Let's restart it. So now I can start it with R. And what you see here, and I also can single step, by the way. Here you see the contents of the RAM chips. And here you see the I/O for RAMs, I/O of the ROMs. Here you see what the register contents are of the CPU. Here you see the stack contents. And there, of course, first I had my simple test programs to see if all instructions work the right way they are supposed to. And here on the right, you see the drum printer that I simulate. So imagine this is a drum that rotates, and every full rotation, it sends an index signal. And this index signal is important because without it, the whole software will not run. And the numbers, so this is the strange RAM design I talked about earlier. Here, for these 4, you need WR0, WR1, for example, these instructions. And these you can access with the usual RAM instructions. And you could, for example, store status information in here, like status words, and the actual number you could store inside here. So input is quite a thing here. It was difficult. So if I press 2 long enough, it should finally get the 2 into the input register. And then if I press S for square root, then it will start to calculate the square root. And here you can see how the calculator actually does it. Here is the result, and look at the printer drum, what it does. It prints the number completely out of order. So it looks what is the current position of the printer drum and which digits I need. And then it activates the specific hammers. So far so good. So now I knew the levels I assume here are the right levels. And with that I was then finally able to build my prototype you could look at downstairs. Exactly. So that's actually everything. Now I was quite under the time. So, are there any questions?
Please raise hand because I will hand you the microphone then. Do you know the initial price of the 4004 when you ordered it?
I think it was $60.
$60, okay.
How big was the firmware? You had 5 EEPROMs?
1024 bytes, and the trick was to implement it in a VM, so it really was a virtual machine. And so they emulated a CPU that is more natural to the calculator functions. And with that, they could save one ROM. And the fifth ROM was only for the square root function. So you could buy the calculator with only 4 ROMs installed, without the square root key, and with 5 ROMs and the square root key.
Do you know if there were other applications for this chipset, for the 404?
Yes, for example, there is an EEPROM burner with this chip. I don't know the name right now, but it's like a suitcase, and you can put one chip in and program with a hex keyboard. And it was also used for traffic light applications in USA, I think. And there was one application for the Keensley taxameter. And the Keensley taxameter used the CPU, and they used another ROM chip. So they only used 2 chips.
How hard is it to find those chips today, and like what's the usual price that you need to pay
The
like, for the
plastic
ceramic
chips-
package, for example?
The plastic chips in eBay you get for like so the CPU for $200, the shift register for like $60, and the ceramic chips, it depends. Without gray traces, like 1,200 or so, or up to 2,000 depending on the condition, and with gray traces up to 4,000 if it's the CPU. And the other peripheral chips, like shift register with gray traces, like maybe 400, 500. And the ROMs you can get for 50, and our prices are a little rising, but you still can get them for $50.
When the manufacturing stopped for these chips?
They were still produced in the early 80s. Yeah. So I think 90 or so, 1990 maybe.
What made it a commercial success? Was it the price, the volume, the calculator
It
itself,
was
the functions?
a combination of the price and the speed. So and it was a little bit faster as other approaches. And actually the chip could have been much faster if the package had been larger. Because then you wouldn't have to do this address multiplexing stuff. You could have sent the address out in one go, and then you could have increased the efficiency. But still, it was fast enough, and there was no alternative. So it really was the first one in this case. And Texas Instruments wanted to bring out their own CPU, but they failed. And also, what made this CPU actually possible? There were 2 inventions from Federico Faccin. One was the silicon gate self-aligned, the self-aligned polysilicon gate. And the other was how's it called? Just said it today. It was some pre-charge for the following MOSFETs. On every MOSFET you lose some voltage, and in some places it is not enough to drive the next gate. And for that he had an invention to dynamically exchange source with drain. You have to imagine if you buy a transistor and bootstrap load, it's called bootstrap load. If you buy a transistor, the position of gate and drain is fixed. But if you have a substrate contact, and then the most negative voltage decides which is the drain in this case. And with that trick, you could construct kind of a charge pump, and then you could increase the voltage to up to I think a factor 1.7 or something like this. Yeah, and what I wanted what I wanted to say is that Texas Instruments didn't use this technology, at least not the self-aligned silicon gate. They still fabricated with metal gates, and for that you needed a much bigger die to incorporate the same functionality. This made the chips harder to design and to fabricate.
Why do we know Intel and not VCFe today? If it was a success, VCFe would have been the brand.
VCFe still had to purchase the chips, and initially they had the exclusive right to purchase the chips, but still it was too expensive for them to keep up. There were already cheaper alternatives, like from Mostec, a single chip calculator. And so Intel bought the rights back from VCFe for $60,000 and then threw the CPU into the global market. Keine Fragen mehr? Dann bedanke ich mich für die Aufmerksamkeit.